All right, now something else that your instructor spent some time on was a separation technique called extraction that's important with acid-base chemistry. So when you're in the lab, usually when you're in the lab, what you're trying to get is a pure yield. That is, you're trying to get one particular compound. But the frustrating thing is that oftentimes many reactions give you multiple yields. That is, they give you a mixture of products, and then you need to separate those products from each other. So an important lab technique is, how do I separate one product from another product? Well, one good technique for that is extraction, using an extraction flask. The basic idea for extraction is that you put two different solvents inside the flask. For example, you might put ether and water. You might put both ether and water. And whichever is denser is going to sink to the bottom of the flask. And whichever is less dense will rise to the top of the flask. I actually don't know who's denser, so I just took a guess. So maybe it's the ether on top and the water on the bottom. All right, and then you add your sample to this. And let's say that you have a sample that's a mixture of A and B. If you have a sample that's a mixture of A and B, what do you want to have happen when you add it to the extraction flask? Well, you want part of the sample to dissolve in the water layer, and you want part of the sample to dissolve in the ether layer, and then they're separated. So this is the whole point of extraction. You're hoping that your combined sample of A and B will separate, where one prefers to dissolve in the water and one prefers to dissolve in the ether. And then you can just slowly let the liquid out of the bottom of the flask, and the ether solvent will be let out first, and what comes out there will be your B sample. And then when you get to the water, you know that's your A sample. Well, what's the basic principle here? What do you remember from the rules for solvation? Does like dissolve like, or does like dissolve unlike?
So like dissolves like.
Yeah, that's the key. So if you have a very polar solvent, would it be better at dissolving polar or nonpolar solutes? Yeah, the polar solutes will tend to go to the polar solvent. Now, this ether might look like this. And we know the water looks like this. Which of these can do hydrogen bonding?
The water.
Yeah. Because it has OH bonds. The ether can't do hydrogen bonding because even though there's hydrogen and oxygen, there's no OH bonds. Well, hydrogen bonding is an indication that you're particularly polar. Water is a very polar solvent, whereas this is less polar. Maybe not completely nonpolar, but less polar. Water is very polar, as indicated by the ability to do hydrogen bonding, and the ether is less polar. Okay. Let's say we have a carboxylic acid. Let's try to figure out, would we consider this polar or nonpolar? Well, it's complicated because there's two portions. There's the carbon chain and there's the carboxyl group. So would you call this carbon chain polar or nonpolar?
Non-polar.
And how about the carboxyl group? That's more polar. So generally speaking, the longer the carbon chain, the more likely it's going to want to dissolve in the ether. And the shorter the carbon chain, the more likely the carboxyl group will win out and wants to dissolve in the water. How could we make this way more polar, however? Well, what would happen if we treated this with a base? We know that if we treated this with a base, it would turn into a carboxylate. Now, is this more polar or nonpolar?
Non-polar. Excuse me, it's...
The big difference is the charge.
It's more polar.
The charge here is a huge increase in polarity. The charge here is a huge increase in polarity, so to speak. Something that's got a charge, we should be thought of as very polar. So now, this is almost certainly going to want to be dissolved in the water over here. So this is an important point. We can make carboxylic acids more soluble in water by treating them with base, because then that gives them a charge. And that's an excellent way to separate them from another solute, because most of the other solutes won't get deprotonated, so they'll just stay in the ether. Let's say, for example, that we had a sample that was a mixture of benzyl alcohol and benzoic acid. We have a sample that's a mixture of this alcohol and this acid, and we want to separate them. Well, notice that we have both of these have a great big 6-membered carbon ring over here. Is this polar or non-polar? The carbon ring.
The carbon ring?
Yeah.
It's not polar.
That's right. So would this tend to drag us into the water or the ether?
The ether.
That's right. All right, so according to your lecture notes here, both of these would be considered only slightly soluble in water. Both of these are only slightly soluble in water because of this big nonpolar ring. So both of them are going to be largely in the ether over here, and they're not separated from each other. If we put both of these into the flask, it looks like both of these would mainly dissolve in the ether. They're only slightly soluble in water, so it seems like they prefer to dissolve in the ether, but then they're not separated. We could call this, so then we would have the alcohol and the acid. They would both be in the ether over here, not separated. So what can we do to get these to separate better? Well, let's add a base, say sodium hydroxide. Let's draw what the benzoic acid is going to look like after it reacts with the sodium hydroxide. What will our benzoic acid look like after it reacts with the sodium hydroxide? Very good. We might draw that as sodium benzoate. Basically, it's turned into a salt. Now, this is a base, so it's deprotonated this acid. Now, who is this more likely to deprotonate, the alcohol or the acid?
The acid.
Right. It turns out that this is not strong enough to significantly deprotonate this alcohol.
So the alcohol would remain in the ether.
You got it. That's right. This is not strong enough to significantly deprotonate the alcohol, so even after we treat this with the base, now remember, we can't separate these. In the flask, these are both, in our beaker, these are both combined with each other, but when we add the sodium hydroxide, that will preferentially deprotonate the acid and not the alcohol. So now after we've added the base, instead of having these two components, we have these two components. And now, when we add these to the flask, where will the alcohol mainly dissolve?
In the ether.
This big carbon chain again is pulling it there. And where will this mainly dissolve?
In the register of water.
So this isn't the acid anymore, now this is the benzoate. Now that it's so polar, it's going to dissolve over here. So this is a clever trick that chemists came up with in the lab to separate mixed up samples. Chemists have come up with lots and lots of clever tricks for doing separations over time, and this is one of the clever tricks. This is called, I believe, extraction. We could say that we're extracting the benzoic acid with sodium hydroxide. We're extracting the acid with the hydroxide, but what that really means is that we're using the hydroxide to make the acid way more polar. So it'll separate from anything else that didn't become more polar. All right, and now we're done. Now we can simply open up the bottom of the flask, and we slowly let out the bottom. Again, I don't really remember whether it would be the water or the ether on the bottom, but assuming it's the ether, as the ether is pouring out, you've got the alcohol, and then in a separate layer, you'll get the benzoate, and now they're separated from each other. And later on, if you wanted to, you could add acid to this component to reprotonate it and make it back into the benzoic acid, and then you've really separated these two things from each other. Okay, That's something that your instructor spent a few slides on. It's a common test topic at this point. You might also, are you taking lab this term too? So you might also do this in lab. All right, so we've learned how we can use the extraction technique in an extraction flask and solvents with different levels of polarity. And the interesting thing is, so the way that extraction works is that you hope that the more polar solute will move to one solvent and the less polar solute will move to the other solvent. But what do you do if both of the solutes move to the same solvent? Well, you don't need to give up. Maybe you can treat the sample with acid or base, and maybe that'll change your charges. So the real big trick here is using base to change the charges so that you change where the benzoic acid wanted to go.